The warm-up for today says, if the table shows velocity data for a car, what is its acceleration? So this is very similar to the types of tables that I gave you in the notes yesterday. Okay, and yesterday's notes you were talking about acceleration by looking at data just like this, or by looking at graphs and describing how the velocity of whatever object was changing per second typically. And that's what this shows as well. So if you look at this data table, it shows 0 through 3 seconds, and it shows velocities that go from 0 to 1.5 to 3 to 4.5. So what is the acceleration of this object? Yes, Austin.
1.5 meters per second squared or per second.
Perfect. It's getting faster 1.5 meters per second every second. 1.5 meters per second every second can be written as 1.5 meters per second, or as 1.5 meters per second squared. It's the same thing, it's a different way to write the unit. Yes, ma'am?
On the problem set last night, on one of the questions, it wouldn't let me type meters per second squared.
If it doesn't allow you to type that in MyFMath, type meters per second.
Like, it wouldn't let you do like the slash numbers.
I will take a look at that with you later. Okay. So again, you can see that every second that is recorded, the velocity gets faster, and it's getting faster by the same rate. And that's what we're going to be looking at in here is uniform acceleration. We're only going to have constant changes to our velocity. It's not going to change by a variable amount because we do not have the math skills in order to analyze that type of problem, because you guys don't, well, I'm assuming you guys don't know calculus yet. I mean, some of you might be in it now, I don't know. But we're going to only deal with uniform acceleration. So that means that my change in velocity is going to be the same each second, like what you see up here. So again, please make sure you enter the answer to the warm-up in MyOpenMath. Today we're going to talk a little bit more about graphs, and we're going to analyze some specific graphs and look at how we can use those to answer questions, or maybe even to get some numerical answers. So a little tiny bit of math there, but after that we're going to talk about the kinematic equations that you're going to be using throughout this unit and really throughout the next several units and even some next semester. And so those are going to be 4 equations. They're super important. You're definitely going to want to write them down. Your homework for tonight is to start working on 202.2 acceleration analysis problem set in MyOpenMath, but it's not to finish it. Because we have more notes over this with more of the math practice specifically planned for Friday. Tomorrow we're not doing notes at all because you're going to be doing a lab. But we're going to return to those notes on Friday, and that's why this assignment is not due until Friday. So I'm encouraging you to start it today, but if you don't feel super confident with the math yet, you might want to save those questions till later and focus on the stuff that you do feel confident about. But you can at least get started on it. Okay, so before we jump into the notes, and today's notes are going to be more of a like question and answer format more than a whole bunch of stuff to write down until we get to the math, then you're going to want to write that part down. But again, you can jot down anything that you learn along the way. So the first question I have for you is, can an object have 0 speed and still be accelerating? Why or why not? Okay, can an object be 0 speed at rest? Okay, and still be accelerating? I see some no's. Okay, guys, yeah, that's correct. You are correct. It cannot, okay, because you can't have acceleration if you're just at rest. Now, could it be momentarily at rest? I guess so. I probably should be a little bit more specific here. But no, you can't accelerate if you're not moving. If you're just sitting at rest, there will be no acceleration occurring. In the notes yesterday, we defined acceleration as the rate of change in velocity. Okay, and we said that that can happen if you speed up or slow down or turn, because velocity is a vector. So if you change either the magnitude or the direction of that vector, you would have acceleration occurring. But in order for you to speed up or slow down or turn, you have to be moving. Okay, and so if you're at rest, you cannot be accelerating. What about this question? Can an object have constant speed and still be accelerating? Is this possible?
Yes.
I hear a couple yeses. I see some people still saying no. Okay. Who said yes? Okay. Why do you say yes? Changing direction, turning, yeah. Okay. If you are at a constant speed and turn, that is acceleration. Okay, so if you're driving in your car down the road and you're approaching a curve in the road and you're, let's say, going 30 miles per hour because you want to be cautious, and you're going 30 miles per hour into this curve, so you start out maybe going north and now you're going east, but you're still going 30, that's still constant speed. Okay, speed doesn't care which way I'm going, it's scalar. So I still have a constant speed, but that is still acceleration because the direction of my velocity has changed. Okay, and so you can still have acceleration when you are changing direction. We have a whole unit on that next semester when we talk about circular motion, because there is acceleration happening even when you have things moving at constant speed if they're turning. Okay, so yes, that is possible, and here's why. This is from the notes yesterday. Acceleration is speeding up, slowing down, or changing direction. All right, so here is a position time graph, and I told you we're going to be kind of question-answer format, which is exactly what you see up here. So we're going to walk through these, talk about them, and hopefully from the notes yesterday, you remember enough about position time graphs and how we can represent acceleration or constant motion on a position time graph in order to answer the questions that you see here. All right, so the first question says to differentiate between Eva and Rip's motion. So take a look at that graph and see if you can figure out what the difference is between the motion that is shown there for Eva and the motion that is shown there for Rip. And if you're not sure, turn and talk to your neighbor for a couple seconds anyway. Make sure they're sure too. But let me know what the difference is in just 20 seconds. All right, guys, what's the difference? What's the difference between their motion? One's accelerating. Which one is accelerating? Eva. So in your notes yesterday, you talked about how when you show acceleration on a position time graph, you have a curve. Because on a position time graph, your slope is your speed. It's technically it's your velocity because it shows you both how fast and which way. But your slope is your velocity. And if your velocity changes, that means your slope changes. And if your slope is changing, you get a curve. Okay, so Eva is accelerating, Rip is moving at a constant velocity. Guys, what happens at 4 seconds? This is a position time graph. When you have an intersection on a position time graph, what does that mean? They pass each other, or they're in the same place at the same time. Maybe they crashed, like in our lab. Okay, but if you have an intersection, they're in the same place at the same time. Specifically, that means here that Eva, who was coming from behind, because she was behind him the whole time, passes him right there. Okay, she passes him right there. Eva passes Rip, they're in the same place at the same time. Maybe they collide, we don't know, but since their motion appears undeterred, we're going to say that they didn't collide, they just passed each other. All right, which person is traveling the fastest at 4 seconds? Who's faster at 4 seconds? They're at the same place. It doesn't mean they're the same speed. Eva has a steeper slope. That's absolutely right, Kyle. Thank you. Eva has a steeper slope right there. I'm aware it's a curve. Okay, zoom in on that tiny little segment, or draw a tangent line if you remember that from your math class. But that's basically zooming in on that small little segment. Okay, whenever you have a curve or an arc. But draw a tangent line in here. The slope of this little segment that you could see, or if you drew in a tangent line, is steeper at that point in time than Rip's is. Obviously, hers is changing the whole time. Okay, but at that point in time, her instantaneous velocity is greater than Rip's is. Okay, so who's traveling faster? Eva is. Her slope is steeper. Which person travels the greatest distance in the first 4 seconds? It's the same. Yeah, good job. It is the same in the first 4 seconds because they're at the same place, about 3 meters-ish, okay, in 4 seconds. All right, at what time do these two people have the same speed? This is a harder question to answer.
3 meters.
Okay, how do we say that we tell speed? Slope. Where are the slopes the same? Again, hers is a curve, but where are the slopes, about where are the slopes the same?
Between 2 and 3.
Between 2 and 3? Here, a 1. At 1, I wouldn't say so. This is definitely a little flatter than this. You're looking for where they look parallel, at least as most as they can. Okay, and I think I called it like here, between 2 and 3 like y'all did. If you put 2, I wouldn't necessarily count that wrong. I put about 2.5, okay, because it looks more parallel to me there, but again, it's a little trickier to see this one. Okay, I couldn't expect you to give me a single value there because it's difficult to tell. But look for a point where their slopes are the same. Okay, so about 2.5 seconds. All right, which person has the greatest average velocity for the first 4 seconds? Before we answer this, how do we find average velocity? Total displacement over total time. So in the first 4 seconds, who has the greatest average velocity? They traveled the same distance, right? Same time, so what will we say? They're the same. Okay, they're going to have the same average velocity. That doesn't mean that their instantaneous velocities are the same. Here, we already said they weren't. We already said Eva's is faster here. But their average over the course of the first 4 seconds would be the same because they have the same displacement and it took them the same amount of time, and so they will end up with the same average velocity. All right, now let's take a look at a VT graph. So we just did some questions about XT graphs, and that's great because it seems like y'all got stuff figured out yesterday with the graphs. Hopefully that's true. If not, hopefully you're asking questions today. But here is a velocity time graph. Okay, and this velocity time graph, you've actually seen it before. I gave it to you in the first unit, but we didn't go as in depth here because we didn't know what Art's motion really was yet. We hadn't talked about acceleration yet. But I've actually just answered this for you. Differentiate between Art and Polly's motion. Art's accelerating. His velocity is changing from 0 to 1 to 2 to 2.5. Okay, if I skip all the way to the end. Okay, whereas Polly has constant speed. Okay, so we would say Polly's moving at a constant speed of 1 meter per second. Sorry. And Art is speeding up. All right. What is the significance of the slope on a VT graph? This was in the notes yesterday. It's the acceleration. Guys, remember, slope is rise over run. Rise, in this case, would be change in velocity over time. Change in velocity over time is the definition. It's the equation for acceleration. So the slope on a VT graph is the acceleration of the object. And if you look at it, Polly's slope is 0, which makes sense. We just said she's not accelerating. She has constant speed. Art, on the other hand, has a slope to this line, okay, of 1/2, because he travels in 2 seconds, he travels 1 meter each 2 seconds. Okay, so rise over run 1 over 2. His is 1/2, so 1/2 meter per second every second. Okay, is how much faster he is getting. And you can see that here with his slope. At the clock reading, t equals 3 seconds, so it's this right here. Who is traveling fastest? Art. Yeah, he's going 1.5 meters per second, whereas Polly is only going 1. It is a lot easier to answer this question here than it is on a position time graph because all you have to do is figure out what the y value is at that point in time. You don't have to calculate anything, you just have to read the graph. Okay, who's going fastest? Art, his velocity is 1.5 meters per second, whereas Polly's is 1 meter per second at that same point in time. What happens at 2 seconds? We talked about an intersection on a position time graph, but now we have a velocity time graph. Are they passing each other? No. This is a velocity time graph. They're not passing each other here. What is happening here? Same speed. Okay, they're traveling the same speed here. Okay, the velocities are the same, so they're traveling the same speed at that time. All right, here is that question though. Who has traveled farthest at this point in time?
Polly.
I heard all possible answers. I heard Polly, Art, and they're equal. One of those is right. Okay, Polly. Now to answer this question, if I ask you, and this by the way was a question yesterday, not this, but a similar one. If you are asked to find the displacement, which is basically what I'm asking, and you're looking at a VT graph, it's the same as it was last unit. Find the area under the line for that portion. So Polly's going 1 meter per second for 2 seconds. She's going to travel 2 meters, but that's the area of that rectangle. Art, on the other hand, okay, is traveling or is speeding up from 0 to 1 meter per second over 2 seconds. To figure out how far he would go mathematically, you would have to take his average velocity. Well, his average, if he goes from 0 to 1, is a half, 0.5, 1/2 meter per second. If he goes that speed for 2 seconds, that is the same thing as doing 1/2 base times height, because I'm doing half of this times this. Mathematically, we end up with the same thing, but it's the area of that triangle versus the area of this entire rectangle. Okay, so Art will have traveled 1 meter because he is speeding up to reach Polly's speed, and he won't have gone as far because he hasn't gotten as fast until the very end of that time period. Okay, Polly has traveled 2 meters, Art has traveled 1. Again, those correspond to their areas, so who traveled farthest? Polly did. Okay, again, if I ask you for displacement and you have a velocity time graph, find area. You're going to have that again today in your assignment, just like you did yesterday. All right, here's the part where you definitely need to write down some stuff, okay? These are your 4 kinematic equations. You do not have to have them memorized. My last class asked me that. No, I'm not going to ask you to memorize them, but I do want you to write them down so that you have them as an easy to find whenever you're doing practice problems, or so that you don't have to like look up this slide every time you're trying to answer a question. So please copy them down into your notes. The first of our kinematic equations, which I've lettered A, says final velocity, which is V sub F, final velocity equals initial velocity, which is V sub I, plus acceleration times time. Okay, so VF equals VI plus A times T. If you need to also label what VF, VI, A, and T mean, please feel free to do that on your paper. Again, that's final velocity equals initial velocity plus acceleration times time. The second equation is final velocity squared equals initial velocity squared plus 2 times acceleration times delta x, and delta x is displacement. Okay, so that's VF squared equals VI squared plus 2A delta x. The third equation is delta x, or displacement, equals initial velocity times time plus 1/2 times acceleration times time squared. Please make a note in this particular equation that only the time is being squared. Please don't square 1/2 or A, it's just T squared. Okay, so this equation again is delta x equals VIT plus 1/2 AT squared. And then the final equation is displacement equals initial velocity plus final velocity divided by 2. Guys, that is average velocity, VF plus VI divided by 2, times time. This equation, equation D, is one you have already seen because you can use it for objects moving at a constant velocity, because your displacement is your velocity times your time, or your average velocity if that velocity is changing, your average velocity times your time. That's the equation I just used when I found the area underneath the curve in my graph. Okay, so it's the same thing. Average velocity times time gives you displacement. Delta x equals VI plus VF divided by 2 times T. So you're going to want to write these down or refer to them anytime you are looking at a word problem, or maybe you're even looking at a graph and you're having to pull information from the graph in order to do a calculation that's not readily apparent in your graph. Okay, and that happens sometimes. Or you're just reading a word problem like some of the ones you're going to see on the next slide. These equations are on the next slide, so I'm going to go ahead and switch it. If I were you, I would write down this example so that you have it in your notes to refer back to. It says, a car is traveling at 32 meters per second when it accelerates to 96 meters per second in 8 seconds. What is the car's acceleration? We have 4 different equations. It is going to be imperative that you identify the information that you have in the question that you're analyzing, which means I just want you to label the stuff that they give you in the question. That's the only way you're going to be able to figure out which equation to use, is if you know what information you have and what you're looking for. So I have some stuff labeled on my screen right now. A G a U, and an E. These are going to be the first 3 steps to solving a kinematic equation problem, is to label your given information, that's the G. We're going to label our givens, identify our unknown. And if we do those 2 things, we should be able to easily choose our equation. Okay, so that's going to be the first 3 steps in what I'm calling, and not, I didn't invent this, but maybe you've used it before, the guess method. Okay, it doesn't mean we're just guessing. It means we're going to label our givens, our unknown, pick an equation, and then I'll talk about the other 2 S's in a second. So, when I read this question, I see a car is traveling. I see 32 meters per second. What is that? It's an initial velocity. It's a velocity first and foremost. If you look at the units, you can see that. Meters per second is a velocity unit. Okay, so if you see meters per second, it's velocity. It's either initial or final, but in this question it says it's traveling that fast and then it accelerates. So that's your initial velocity. The next number I see is 96 meters per second. Is this a velocity or an acceleration? It's a velocity. It says it accelerates to this. This is my final velocity. Sometimes students see the word accelerates though and they're like, oh, that's my acceleration. No, it's not. If it were, the units would be meters per second squared. Okay, please check the units. Make sure that you're labeling it correctly. Okay, so it accelerates from 32 to 96, which by the way is not realistic for a car. That's way too fast, but that's okay. In 8 seconds. 8 seconds is what variable? Time. Again, you should recognize that unit. So we have VI, we have VF, we have T. That's all we have. And then we're looking for acceleration, because that's what the question says. What is the car's acceleration? If you go through the process of labeling these things, I promise I'm not giving it to you just to make extra work. Okay? It's because this is the way you're going to determine which of those 4 equations to use. If you now look over here, you need to find a way to solve for acceleration when you know VI, VF, and T. So looking at these, if I start, up here with the first one, here's VF, I know that. Here's VI, I know that. Here's T, I know that, and I'm looking for A. That's the equation you're going to want to use, is equation A. But let me talk through the other ones real quick to show you why you can't use them. The second one, I have VF, I have VI, I'm looking for A, but I don't know delta X. I can't use this equation because there are 2 things that I don't know. Okay, now if I had delta X, yes, I could use it, but I don't. So I cannot use equation B because there's 2 things I don't know, A and delta X. Equation C, again, there's delta X, can't use it. I don't know delta X. Okay, equation D, again, has delta X in it. However, I could actually use this equation if I wanted to solve for delta X because I do know everything else. I know VI, I know VF, and I know T. So if you wanted to, you could use equation D, find delta X, and then use equation B or C to find A, if you wanted to do it and do twice as much work. But there's always a faster way, and then there's a slower way that takes more steps. There's more than one way to do this. Personally, I would prefer to do it in 1 step instead of 2. So that's what I'm going to do. But it is possible to solve these in 2 steps if you solve for the other thing you don't know, because there are 5 total variables in these equations. VI, VF, A, T, and delta X. Typically, you're going to know 3 of those things and be asked for a 4th one. Okay, so that means that you could always do these in 2 steps, or you could do them in 1. I'm going to use this equation. VF equals VI plus A times T. So now I've done the first 3 steps of my guess method. My givens, my unknown, my equation. The next step is substitution. Substitute in your numbers. 96 equals 32 plus A times 8. Okay, and you should, before you substitute in, double check your units to make sure that they match each other. Mine do. I have meters per second, and seconds, so I'm good. Okay, but you would want to double check those. Okay, so now from here, I have to solve. That's the last S in the guess method. Okay, so we're going to do the algebra. Speaking of algebra, looking at this equation, obviously I need to solve for A. Okay, 96 equals 32 plus 8A is basically what I have. Can I add 32 and 8A together? No. And yet, despite the fact that you can't do that, somebody always tries to. Okay, so please do not add them. They are not like terms. You can't do that. Okay, so the first step is moving 32 out of here. I do that by subtraction. Subtract it from both sides. 96 minus 32 is 64, and it's equal to 8a. Now, if I want to get a by itself, I simply divide both sides by 8, and that gives me 64 divided by 8, which is 8 meters per second squared. And again, I can see that because these units were meters per second, and I just divided them by seconds. So meters per second, or meters per second squared. Questions about this example? All right. Here are 2 more examples. Okay, I'm not going to work the whole thing out. However, I do want you to take a moment to read the first question and see if you can just label the variables. Because honestly, if you can do that part, that's like half the work, is picking the right equation. Okay, and labeling the variables is the first step. So let me read the question to you. It says, an object has an initial velocity of 4.0 meters per second and a constant acceleration of 2 meters per second squared. How far does the object travel in 20 seconds? So again, I'm going to give you a moment to label this, do the givens and the unknowns on your own. And if you want to, you can even try to pick the right equation. Okay, but do this on your paper, okay, so that you have it to look back at. I'll give you a moment to do that, and then we'll talk about how you should have labeled it, what information you have, and then we can determine our equation from there. Okay, so I was really nice with this one because I kind of labeled it for you by the way I worded it. An object has an initial velocity of 4.0 meters per second. That's obviously VI. Okay, it's labeled for you. And a constant acceleration of, again, I was nice there. There's my A. So you have VI and A. How far? What does that mean? Delta X. I'm looking for delta X. How far? Delta X question mark, that's my unknown. How far does the object travel in 20 seconds? That is, of course, time. Okay, so now we have our variables, VI, A, delta X, and T. Specifically, you're looking for delta X. You have the other 3. Okay, I'm going to let you try to figure out your equation so that you can solve, but when you do solve, if you do it correctly, you should get 480 meters. So you can make sure you got that number, and if you didn't, then we can go back and look at what happened. Okay, but before you do that one, I want to now take a look at the second one and see if we can label that one. Okay, we're going to label them both, and then you can work on them at your own pace. Okay, the second question says, a soccer ball rolls 110 meters to a stop from a speed of 21 meters per second. What was the ball's acceleration? So I'm going to go piece by piece. A soccer ball rolls 110 meters. What is 110 meters going to be? My displacement. Okay, so it rolls 110 meters to a stop from a speed of 21 meters per second. Okay, what other pieces of information do you see in that sentence? An initial velocity of 21. Okay, what else? Anything else? I'm looking for acceleration. But if that's all I have, that's not enough information to solve for anything. There's one other piece of information in that question. Anybody see it? To a stop. Guys, what does it mean if you come to a stop? It means you're not moving. It means you know a velocity. If you see words like comes to a stop, rolls to a stop, you slam on your brakes until you stop, that type of thing. If you see stop, okay, it means 0. It means they're giving you a velocity. Okay, we had the initial there. We're looking for acceleration. Okay, but if you see comes to a stop, it's a velocity. It's your final velocity. The same is true if you see the words the car starts from rest. What does from rest mean? 0. I don't have that here, but you'll see that in the questions. A car initially at rest speeds up or whatever. Okay, so be careful and look for words like comes to a stop or starts at rest, because those are actually telling you pieces of information, and they mean a number even though the number is not written in the question. So it's easy to overlook, so just read it carefully. All right, so again, try these 2 questions. By the way, the answer to the second one is 2 meters per second squared. But if you're not getting the answers that I have up here, Okay, then we need to figure out why. But your first step after doing this is to choose the appropriate equation. Okay, so again, take a look, see if you can figure out which equation to use in order to solve this, and then that will help you obviously as you're getting to that answer. Does anybody know which equation to use for the first question? C? Let's take a look. We have VI, we have A, we have T, and we're looking for delta X. So let's look at C. VI, A, T, delta X. Perfect. Yes, you're going to use equation C for the first one. Okay, what about the second one? I know some of you haven't started that one yet. That's okay. Take a moment and look at the second one. Figure out which equation you should use.
For the second one, what's the answer negative? Was your slowing just stop?
You are correct. It should be. Thank you. But which equation should we be using?
B.
B. Yeah, we should be using equation B. Okay, because we have VF, we have VI, we have delta X, we're looking for A. Obviously this one's not set up to equal A, so you're going to have to rearrange it. But that is the equation you should be using, and yes, Drew, I think you're the one who pointed out the negative sign, right? This is, I did forget a negative sign here. What is the ball's acceleration? It should absolutely be negative because it's rolling to a stop. Okay, so this should be -2, not just 2. Okay, I will double check that. But again, go ahead and work out these two. Make sure you get these answers, and then if you have done that, what you're doing after that, and I'll go back in a second, but you're going to go to My Open Math to work on 202.2, Acceleration Analysis Problem Set. This assignment is not due until Friday, so please don't freak out about it if you're not sure about how to do them. If you don't know how to do a question, skip it. You're going to have more class time to talk about it on Friday. Okay, so try it now in class. If you get stuck, ask for help, or save that question for later. But if you have any questions, please let me know.